Now in the second part of this video lecture, we're going to prove that the integral that we defined for simple measurable functions, simple functions. Now in the second part of this video lecture, we're going to prove that the integral that we defined explicitly for simple functions, it has the property of being linear, and we start by proving this lemma which will be used in the proof. What does it mean to be linear? Of course, linear means exactly that the integral commutes with sums and multiplication of by scalars. And from linear, that this integral is unitary, it is clear from the definition. There's nothing to prove about being unitary. So we'll prove that it's linear. And monotone is also clear, because since it is linear and non-negative functions, when we plug them here, these will always be non-negative numbers. And by linearity, monotonicity follows immediately from linearity. So you really just need to prove that it's linear. What we have seen already is that we defined, when we write a function f as a sum of numbers multiplied by indicator functions of sets that form a partition, and these are distinct numbers, when f is of this form, then its integral is given by summing over all j's, all indices j's, the product of this little number here by the measure of the set here. And now the lemma is the following. This is still true without assuming that these a's are distinct. And that's a very simple and immediate property, but we'll use it in the proof of linearity. So again, instead of giving a formal proof, let's do a picture. Before, we were assuming that these aj's were distinct. Let's see, a1 here, a2, a3, a4, a5, and here we have a partition. 1, 2, 3, 4, 5, okay. And we know this partition just corresponds to the pre-image of these points under the function f. So f goes like this. And this was all working very well, because there's only one way to, if a function is simple, then of course the places, the subsets where it takes the same values, they form a partition. So except by permutating indices, there's a unique way to write the function like this, and that's how we defined the integral like this. And now we want to relax that, and because we're going to prove linearity and we will need to relax that. So what we assume now is we don't assume anymore that these aj's are distinct. What do I mean by that? I mean, well, here, let's write here a8, a6. Let me write here a6. a6 equals to a1, so they're not distinct anymore. But we still have a partition, except that now I'm going to divide this set here, and this part I will associate to a6, and this part I will associate to a1 in a rather artificial way. This is not really related to what the function is doing, because the function is just sending every element from this partition to this number. It does not care whether we call this number a1, a6, or both, but it is important when we write the function in this form, that f equals the sum over j of aj, indicator aj. This is still true, even if I call this set here a6 and I call this set here a1. It is still true that f is written this way, and it is still true that these sets form a partition. The only condition that I'm losing here is that these aj's are no longer distinct. So now I have a larger partition with 6 sets instead of 5. Okay, 6 sets, 2 here and the other 5. This expression is still true, except that this expression is a bit redundant. It's not the most economic possible way of writing f this way, because I'm considering 2 sets here in the partition where the function maybe takes the same values. But it's okay. It will, of course, give the same value for the integral, Why? Because here we're just really decomposing a set of the partition into two, but the measure is additive. So this will all cancel out here in the end. Or said differently, when we compute this sum, we can group terms. So when we're writing this sum here, we can first group sets here that correspond to same AJ. When we group them, then we get the sum of the indicators. And when we compute the measure, we have the sum of the measures. The sum of the measures is the measure of the union, and this will work. Let's omit the details. This should be quite obvious. So now we want to prove that this definition is linear. What does it mean? It means if f and g are simple functions on the same measure space, then this integral that we have just defined is linear, even if we let's add a little constant here and a little constant here, a and b. This is the same as. So now we move to the proof of linearity, and what we mean by that, we mean if we take two simple functions on a measure space omega f mu, and we compute their integrals, then we can do linear combinations of their integrals, in the sense that we can integrate f, we can integrate g, and we can wonder what is the result of multiplying this number by a, multiplying this number by b, and adding them. And we can wonder, is this the same as considering the function af plus bg? This is a function. This is also a simple function. So we can integrate it using the same formula that we have just presented. And we can wonder whether these two things are equal. Of course, we expect them to be equal. We want them to be equal because this means this integral we just defined is a linear operator. And this is what we're going to prove now. For that, we write f equal the sum where j goes from 1 to n of aj, indicator of aj. And we can write g, and I'm going to use different indices because I'm going to mix them soon, and it's better to have different indices, even if it doesn't matter at this point. Going from 1 to k, not n, of bi, indicator of ai. We can write them like this because by assumption they are simple. And now how are we going to use this previous lemma that we just proved, that they do not need to be distinct? It is bi here. It is these sets aj, they form partitions. These sets bi, they form partitions. And if we cross these partitions, and we may, so here's the partition aj's, here's the partition bi's. We can of course define a partition indexed by both a and I and j. So you can consider ai intersection b, or aj intersection bi, and let I and j vary on this set, which is also a finite set. So this is a partition. And this is all that matters for us, that this is a partition, because by the previous lemma, we need to work with a partition. And now, of course, we can write the function f, which is this. We can write it as f to be the sum, when j goes from 1 to n, of aj. But here, instead of writing indicator of aj, I want to write the sum when I goes from 1 to k of the indicator of aj intersection bi. So I'm just decomposing. So this was j here. I'm just decomposing it like over I, writing this indicator like this. This is very convenient because we know these are all finite sums. So we can now take this a inside the sum, And we can do something similar for G. So we can write both f and g in a much more convenient way. Let's clean this mess a little bit. We can have, again, f to be the sum over j. It was aj, indicator of aj, but now I'm going to take the intersection with bi and summing over I. We can do that, as we just described, and we can do the same thing for G. So we can write G as the sum over I, and then the sum over J of BI, indicator of BI intersection AJ, but let me write this as AJ intersection BI, just to be consistent. And let's also swap the indices here and sum over J first. These are finite sums, they always commute. And all that just to say, well, we're going to do now AF plus BG, and all this work is just so that now we can really group them. So this now becomes, we sum over J, we sum over I, then we have AJ plus BI times this indicator. So all this work was just to get this. Oops, this was without the constants A and B here in front. If we want to add these constants, so if we want to add to multiply by A, then of course we just multiply by A here. And if we want to multiply this by B, we can just put the B here, which means we can put these constants A and B here, so we get them inside. Oh, we can get them here inside. And here is when we use the previous lemma. We want to compute the integral of this simple function. Well, this simple function, it is being written as the sum over a partition of numbers that are indexed using the same indices as the partition, except that now here my index is a pair ji, but it doesn't matter. We know by the previous lemma that this integral will be equal to, we sum over j, we sum over I, it will be a I j plus b bj of this indicator, a j intersection bi. And now that we have this, now we can split these back. We did all the work to put them together. Now we will undo all that work. This will become the sum over j of aj. Oops, no. Sum over I of aj, indicator of aj intersection bi. And the same thing for the b part. But now what we can see is this intersection with bi's, they form a partition. So if we remove this and remove this sum, it won't change the result. This is basically what we have done already. And well, except we are computing the integral. When we compute the integral, then here we should get the measure mu instead of the indicator function. So we should be really talking about a measure here. Not an indicator function. But this still works because we're just decomposing aj as the disjoint union of the aj intersected by all the bi's, so we can compute the sum. And this is just the integral of a f. And this part we do exactly the same thing, but we'll be canceling the sum over j rather than the sum over I, and this will be the sum, the integral of bg, the mu. So this is how we prove that the integral is linear. This is how we prove that expectation is linear as well. And well, this rather long and tiring video lecture is finished.